mountain range, apparently. So just ridiculous density. And obviously, anything of our stature would be squashed beyond recognition on the surface of a neutron star. What's interesting is that even though the temperatures can be really very high, particularly in the early phases of a neutron star, nonetheless, this could still be below the characteristic transition temperature to form either a superfluid or a superconductor, it turns out, in the interior. And so if you actually look at some of the numbers, like for the neutrons to form, now by the way, neutrons are fermions, so how would they form a superfluid? So they actually apparently can actually undergo a pairing interaction where you can actually pair the spin up with a spin down neutron, so you have a net spin of 0, and these can then actually condense to form the superfluid. And so notice I write down some numbers that I've got from the literature. So this is a TC of 500 to 800 million Kelvin versus the all-time record that we have for superconductors here on Earth. And this is even under pressure. I think it's around 200 Kelvin, something like that. It's for some compounds. I think it's some hydrogen. I think it's actually hydrogen sulfide compounds that somebody was able to compress under very high pressure and actually get it to become superconducting with it. At atmospheric pressure, the highest, the world record, I think, is around 150 or 160 Kelvin, somewhere in that range at 1 atmosphere of pressure. So you can look at these numbers. Protons can form a superconductor with a TC in the 2 to 3 billion Kelvin range, and then quarks. You can actually, because of the QCD interactions, the quark-gluon interactions and so forth, you can actually get what they call color superconductivity, apparently, because you have the 3 different quote-unquote colors of quarks. And the TC there is in the 25 billion Kelvin range. Okay, now, what about numbers? There's some other numbers that I was able to pull out of the literature, and or maybe do some back of the envelope estimates on some of these, but coherence length. So this is one of the things that I didn't go into a lot of detail about. There's a thing called the Ginsburg-Landau coherence length. It's essentially the characteristic length scale over which the order parameter could potentially, let's say, have a boundary between a normal and a superconducting region, like if you currently have at the core of a vortex, for example. And in the high TC superconductors, that coherence length, it's already pretty relatively short, but it's in the range of about maybe 15 angstroms, something like that, in high TC cuprate superconductors. Well, apparently in these color superconductors, that coherence length is more like 27 femtometers would be the sort of unbelievably short coherence length. Okay, what about the BCS energy gap? So apparently, okay, you do have a BCS-like pairing mechanism. I mean, not exactly BCS, but pretty much a BCS theory would apply to these different systems. The BCS gap in a by comparison in the cuprate superconductor, which is already pretty high compared to your low TC superconductor, is going to be in the range of 30 milli-electron volts. And here you can see that the gap is pushing up to in the 100 mega-electron volt range. So it's just, the numbers are just absolutely staggering. And I want to point out that because of this superconductivity or superfluidity in these systems, that means you can get the same things you get in a regular superconductor. You get, like in the case of a superconductor, let's say neutron star or quark star superconductor, you can get Abrikosov vortices that carry magnetic flux. And because of the short coherence length, that means that the upper critical field is going to be absolutely astoundingly high. And I don't know enough about to say with certainty, but I believe or I suspect that these things that some of you might have heard of called the magnetar, which have fields that are in the, I'm trying to remember if it's in the billions of Tesla or how big those fields are, but anyway, these unbelievably humongous magnetic fields that would just, even if one of these things was rotating within some fraction of a light year of Earth, it would be enough to wipe out life on Earth, apparently, I guess, in other words, these magnetars. So I think that maybe because of trapped Abrikosov vortices or trapped flux in these things, that why they have such a humongous magnetic field in those systems. Now, okay, there's theoretical, so people have predicted these things theoretically, but the question is, well, how do we know, or at least what evidence do we have that these things actually exist? So this is actually where they're talking about this pairing, I guess, pairing of neutrons. Well, apparently, one of the things that they see, they see a set of phenomena which they have a very hard time explaining any other way, except in terms of these either superfluidity or superconductivity. Some of them are rotational glitches, where the thing will just, it'll be rotating at some ridiculous speed, rotational speed, like 1,000 hertz or whatever it is, and suddenly you'll see a rapid glitch, just a sudden change in rotational speed. And they really don't know how to explain it except for maybe one of these vortices sort of escaping out or vice versa. I think it's probably escaping out, like some of these vortices. By the way, in the superfluid, you have vortices as well, except even if it's not superconducting, except it's not something that carries magnetic flux. It only carries angular momentum, but otherwise it has some very similar properties. The other thing that apparently they've seen, for example, this is one that I saw a paper online, I guess it was this paper here, is they apparently see evidence for a very rapid cooling. And I think the way they explain that is that when you get the pairing taking place, it gives off massive numbers of neutrinos, and that releases enough energy that actually causes the thing to cool down quickly, apparently. And so there's a number of things that indirectly provide evidence for the existence of these superfluidity and superconductivity in neutron stars, essentially. Okay, the rest I think I'm not going to worry about that for now. Okay, one thing before I forget, okay, I sent you a little info, it's probably incomprehensible, but about this guy, A. Garrett Lisi's scheme, or ideas about using group theory in Lie groups, this very massive group called the E8 group is a way of supposedly trying to relate, sort of tie everything together. There's another guy who's kind of another brilliant person by the name of Juan Maldacena, who, now the thing that's interesting, Garrett Lisi is way outside the mainstream, and his paper has only been, it's on the archive, it's only been, I mean, it's been cited a good number of times, but not a humongous, it's been cited 131 times or thereabouts. If you contrast somebody with somebody that's a little bit more, much more in the mainstream, who's at Harvard, his name is Juan Maldacena, one of the things that he did is he came up with a way of supposedly mapping general relativity in a certain number of dimensions. I forget how it goes. It goes from 10 to 11 or vice versa. So in other words, mapping general relativity in a certain number of dimensions to conformal field theory in a different number of dimensions. So one of them is in 10 dimensions and the other is in 11 dimensions. Now why would that be useful? Well, apparently, I guess it's very exciting because it maybe that gives you a way of potentially tying things together, but another thing that makes it exciting for people is that apparently it makes some things that are almost impossible to calculate in some limits for, let's say, using conformal field theory. If you map it in this way, it becomes much easier to calculate using the general relativistic approach in the other different number of dimensions, and vice versa. In other words, sometimes something is impossible to calculate with the general relativity approach becomes much easier to calculate using conformal field theory. And apparently, as a mathematical tool, people have even used variants of that scheme, even in condensed matter physics, where they find a problem that's just like impossible in condensed matter physics, so they map it into something that's where you use general relativity apparently, and they find, oh yeah, I can actually do some nice calculations based on that. Like there's a guy named Philip Phillips. He's a brilliant African-American physicist at University of Illinois at Urbana-Champaign, and I've seen some talks by him where he's given some, he uses this scheme, or schemes like that in condensed matter physics. And so, anyway, looking at general, so now, one of the things that, okay, principle of equivalence right here. So one of the things I guess I'll mention, since we kind of going back to special relativity, is that it turned out it wasn't so difficult to combine quantum mechanics with special relativity. And so essentially what happened was that it required some, well, I should qualify that statement. So for example, Paul Dirac, back in the 1930s, he was able to come up with a relativistic wave function, essentially, a relativistic version, in other words, replace the Schrodinger equation with a relativistic equation that we call the Dirac equation. I should qualify that there were some complications in that he had to split up his wave function into like a column vector that has several different components, and essentially 4 components. And I guess maybe that had to do with the fact that if you're trying to do this in a 4-dimensional space-time, you had to, there were some nuances associated with how do you construct fermionic particles that, that still obey the principles of special relativity. And so there are all these things you have to somehow, you have to make sure that your thing is covariant and there are Lorentz transformations and so forth. Now, before Dirac came up with this equation, there were what's one called the Klein-Gordon equation. It was more just a regular wave equation, and that worked okay if you're talking about bosons. In other words, it didn't work so well when you're talking about fermions, but it worked okay for bosons. Now, what happened in the Dirac equation is that when you split up the different components of your wave function into these 4 terms, I think what ends up happening conceptually is you think of them as being equivalent to spin up and spin down of positive energy guys, and spin up and spin down of the negative energy guys, and those are the things that he ended up postulating would represent antiparticles. And by the way, in some very crude sense, one I guess can think of the Dirac equation as being kind of like the square root of the Klein-Gordon equation. And by the way, let me just remind you, see if I can remember here, E squared is equal to m squared c to the So the question is how, this would be our classical equation for the energy right here. How would you get something that looks quantum mechanical, from that? And so you'd say, I want to construct operators. Okay, this would be like a momentum operator right over here. This is the rest mass energy right here. This would be something that would be like, that would go, you try to construct some kind of Hamiltonian operator based on that. And so with the Klein-Gordon picture, that wasn't so bad, but the problem is it didn't seem to work for fermions. And so you can take the square root of this thing, but then it's like a mess. And so that's where things turned out to be really tricky. So that's why the Dirac equation was kind of a major achievement, to be able to figure out, how do we come up with a relativistic way of combining relativity and quantum mechanics, essentially. And then that was extended into quantum field theory. So like all of quantum field theory, you're basically expressing things typically in relativistic form, as long as you're talking about it, using it in, let's say, particle physics and so forth. And so that was fine. Now, when you attempt to try to combine quantum mechanics with general relativity, that is where it's like a whole different kettle of fish or kettle of worms in that case, because when you are curving space and time, that means when you start to try to think of it quantum mechanically, even the distinction between past and future becomes very difficult. How how do you even define the distinction between past and future if you start to think of things from a quantum mechanical point of view? So that has actually been one of the paramount difficult problems in physics, is combining quantum mechanics with general relativity, and then at the same time trying to explain, sort of unify the four fundamental interactions or forces in nature, and as well as all the particles. Now, if we go back to just classical general relativity, the principle of equivalence, okay, it's an extension of his first postulate of general relativity, but the idea was, what do we mean by principle of equivalence in the context of general relativity? Well, what he argued in the case of general relativity is that if you go to the, actually, I think the next slide actually goes into that right here. So what he argued is that if you are inside a small room, and if you're standing on the surface of the Earth, where you experience a force, essentially, of 1g, or of mg rather, with a force pulling you down toward the floor, as far as you're concerned, that would be completely indistinguishable from the case where if you just had a rocket ship, if you're inside a rocket ship that was accelerating out in space at a rate of 1g, you would still feel like you're being pulled down to the floor. And so what Einstein argued then in general relativity is that he said, okay, well, somehow these reference frames should be equivalent, like an accelerated reference frame should be equivalent to being in a reference frame in which you have a magnetic field, in which you have a gravitational field present. Okay, okay, here we go, principle of equivalence. So there's no experiment that can be done in a small confined space that can detect the difference between a uniform gravitational field and an equivalent uniform acceleration. Now, here's the other thing. Remember that you go back to your 1321 class, you remember Newton's second law, F equals ma, but you could actually, and then remember we said, okay, for the force, gravitational force, we said it was mg. Well, what's interesting is that if you wanted to, you could actually define these m's differently. You could say m in the first one, F equals ma, is just the inertial mass. We could say this is the gravitational mass. These don't necessarily have to be the same. And if we were to compute the acceleration of something in a gravitational field, it would be this guy, it'd be the ratio of these things times g. Now, the idea from experiments, we know that as far as we know, these things are exactly the same. In other words, that this ratio is 1, and so that A is exactly equal to G. And so that would be consistent with this idea of the principle of equivalence, that inertial and gravitational masses are exactly equal, basically. And then the other thought experiment that I guess he did was, imagine, okay, suppose you have a light beam and you have this accelerated reference frame, and you allow light to pass through. You would see that the light would be bent as this thing is being accelerated upward. It would look like it's being bent. And so then he argued, okay, the same thing should happen when light comes into the presence of a gravitational field, that you should see bending of light. And so then finally he started to argue that, well, okay, think of gravity not as a force, but as a curvature of the fabric of space-time in some sense. And the way this was represented was using differential geometry. Some of the ideas I think were developed by, well, some early ideas were developed by Gauss, but then later further developed by Riemann. And so you start to think in terms of tensors, actually. You start to think in terms of describing this curvature of space-time in terms of basically these various types of tensors. And so here, the idea is that, okay, mass energy, there'd be a mass energy tensor, in other words, that would describe how how does that cause space-time to curve in some sense. And then once you have that curvature, that would tell you how matter would end up behaving, I guess, within that curved space-time. And so I'm gonna do a Google search, I think, after we go through these slides. If they don't actually write it down, of the Einstein, just do a Google search later, but I'll probably do that here if there's time, or maybe I'll wait till next time. Of the Einstein field equation. There's actually a very elegant way of writing it down in terms of tensors. Of course, actually understanding what goes into those tensors is a whole different matter. Okay, so that was actually first carried out in 1919. Now, this is actually used pretty routinely. The bending of light, they thought it would have no practical significance whatsoever, but from the point of view of understanding certain things about our universe, it's had a huge impact because, okay, here it's minuscule. The amount of light bending that you see, just light going around the sun even, is not that great. But when you start to talk about galactic clusters, galaxies and galactic clusters, the extent to which light gets bent becomes absolutely humongous, to the point where you have dramatic distortions of galaxies that are behind whatever it is. It could be a mass of dark matter, for example, in front. So you can even use it as a way of detecting dark matter, for example. And so whatever you have in front can act like a gravitational lens that actually magnifies the stuff behind it, or distorts drastically whatever you have behind it. In fact, here's an example. So gravitational lensing. So this would be, for example, light from a distant quasar passes a nearby galaxy. It's actually bent in different directions. So you actually, in this case, you see multiple images of exactly the same quasar around this gravitational lens in this case. The other issue is that light coming up from a very massive object tends to redshift quite a bit. And from the black hole, it becomes ridiculously, but eventually it becomes infinitely redshifted once you get right at the event horizon. Okay, so apparently somebody actually was able to measure the opposite effect, which is a blue shift effect, and gravitational time dilation. I think they actually depicted this kind of a very large-scale example of this in the movie Interstellar, where they were orbiting around a black hole, and the people that were closer to the black hole, there was so much gravitational time dilation that the guys were there for, what was it, an hour, I think? And then meanwhile, they finally make it back to the other spaceship that's further away, and the guy is aged by, I forget how much, what it was, like 10 years or several years apparently, but it was a lot. In other words, so there was a huge gravitational time dilation that they depicted in the movie Interstellar. And essentially, again, this time dilation becomes essentially infinite for things that once they reach the event horizon of a black hole. And the idea is that if that's a big if, you were able to watch something falling into a black hole, they would appear to be just sort of frozen forever right at the event horizon because of that infinite gravitational time dilation. That was actually kind of an astounding achievement by Albert Einstein, was to actually be able to show that his theory was able to explain this anomalous perihelion, this anomaly in the orbit of Mercury, which you could not explain using Newtonian gravitation. Why do I say that's a tremendous achievement? Because he did not have the benefit of digital computers. He was able to do it somehow with pencil and paper, basically do these calculations and actually show that yes, you can actually explain the perihelion of Mercury within the framework of general relativity, and that was something that was not explained within the framework of Newtonian gravitation. Retardation. Okay, so I guess just showing the difference in optical path, effectively the distance of optical path lengths in this case. And oh yes, okay, LIGO. We will have the director of LIGO coming out here October 23rd, hopefully if all goes well. So I hope that everybody, I'll try to make sure, I hope that the department will make sure the department sends out the announcement about that. So he will be giving, I'm guessing, 2 talks. One will be like a colloquium. Will be here. He's my former fraternity brother, David Wrightsey. He'll be giving a colloquium here in our department, and then giving a more general talk for the public, which should be a little bit easier to follow for a lot of the lay people at one of the larger lecture halls on campus. We don't have the details worked out yet, but so that'll be coming up October 23rd, hopefully thereabouts, if all goes well, 23rd, 24th. And this here, they're talking about predicting gravitational waves. I'm sure you heard about the announcement that was made of the observation that took place, I think, in September of 2015. There's been subsequent successful observations since then, at least one that's been published. So in other words, there's not just that one, so there will be more, and I think they'll be talking about. So that's pretty exciting. The first one, of course, was that merger between these two massive black holes around 30 and 31 solar masses that I guess that merged together thereabouts. And the second one is actually somewhat smaller black holes, at least that I saw published. So that's a pretty exciting event. So that's all like a whole new field of astronomy now that's emerging there. So these are a little bit outdated. I guess I wonder if they have LIGO. Okay, I guess they don't really mention LIGO in here. Oh yeah, no, they do. Yeah, LIGO right there. LIGO right here. Here we go. Okay, so there are two LIGO systems that here in the U.S. at the moment. One is in Louisiana, and the other is in Washington State. And so, since these two detectors were able to detect the gravitational waves that were separated by a certain amount, I forget how many milliseconds, and they were able to infer, I guess, enough information, they were able to kind of partially locate the source, but not completely, because you need really at least 3 different detectors to do that. But at least they were able to partially locate the source of the merger in the sky within some arc. In other words, kind of partially determine where that was. Once you have additional detectors being built around the world, that'll give us much more accurate information about how to pinpoint the sources of these gravitational waves.
We can locate gravitational waves.
Yeah, or yeah, where they come from. In other words, where the black hole collisions to where they take place or took place. And okay, that's you can actually amazingly I think you actually get that same result if you just do non-Newtonian calculation of escape velocity. Just set that equal to the speed of light, and then set the distance equal to r sub s, and you get that same exact result. Just set. Remember, I think you have to calculate the escape velocity. You just set 1/2 mv squared. You did the classical in the